Okay. All right, welcome to yet another graduate seminar. We have, once again, Bhavneet Singh talking about rational tangles and knot theory. This is the second part to his talk, so I'm assuming he will give a brief introduction again, just a recap, and
Yeah,
then...
we'll do a recall.
Okay, take it over.
Thank you. Okay, so the first talk, we introduced what are rational tangles, and then we looked at Conway's theorem, and we proved one direction of Conway's theorem. So, first of all, an overview of this talk. So, we will recall what we did last time, and then we will move on to a new definition of a new invariant of knots, which we call a conductance invariant. We will motivate its definition and look at its formulation, and then we will define the conductance invariant for rational tangles. Then we will use that definition to prove our Conway's theorem, and if there's still time, we can look at one of the applications in biology. Okay, so first of all, what are rational tangles again? So we defined rational tangles in terms of integer tangles. So the integer tangles looked something like this. So this is an integer tangle T3, T negative 3. So this is an integer tangle. This is a horizontal integer tangle, and T dash would be a vertical integer tangle. So it will look something like this. So this will be our vertical integer tangle denoted by T dash. Okay, so this is how we define the rational tangles for ourselves. And
just to make sure, what about it makes it 3 again?
I'm sorry, it's we twist it once, that's T1, and we twist it again, that's T2. I'm sorry, yes. So this will be T negative 2, and we look at it in the plane of the paper. So if we are coming out anti-clockwise, it's negative. If we are going into the plane of the paper, then it's positive. That's just convention for us. And using that, we defined that any tangle that is basically a sum of integer tangles gives us a rational tangle. Then Conway gave a theorem that two rational tangles are ambient isotopic if and only if their fractions are equal. So recall that last time we associated a fraction to each of the rational tangles. To look at it, from the definition of the rational tangles and some operations that we defined on it the last time, we found that every rational tangle can either be represented like this or this, where tan minus 1, so on up till ta1, these are all the integer tangles, horizontal integer tangles. So the next step was to just remove tan and just write an is an integer here. So this is a continued fraction form which gives us a fraction associated with a particular rational tangle. So using that, we associate with each tangle a fraction. Now we need to show that this fraction that is obtained from the continued fraction form is indeed unique for each tangle, each ambient isotopic tangle. So to do that, we proved the one direction of Conway's theorem, which said that if T1 and T2 are basic tangles are nothing but these. Every rational tangle can be represented as basic tangles. We did that the last time. And then we have Conway's theorem that tells us that if T1 and T2 are basic tangles, and if the associated fraction for T1 and T2 is equal, then T1 is ambient isotopic to T2. They are in the same equivalence class.
Can you remind me again what basic tangles?
So basic tangles are like, it's just a convention of how we want to generate the tangle. So we start with the horizontal integer tangle.
The recursive definition.
Yeah, the recursive definition. Is that okay?
Yeah.
Okay. So what we did in the proof was that first we showed that there exists a continued fraction form called the regular continued fraction form, which is uniquely determined for a given rational number. And then we showed that there exists a formulation which allows us to change any continued fraction form into a regular continued form. And the last step was just to show that that change does not change the ambient isotopic class of our rational tangle. So this way we proved one direction of Conway's theorem, that T1 and T2, if T1 and T2 are basic tangles with fraction of T1 is equal to fraction of T2, then T1 is ambient isotopic to T2. Now the opposite direction, that if we are given that the two tangles are ambient isotopic, then they have the same fraction. We need to show that they have the same fraction. So for that, first of all, what we will do is that we will define a polynomial invariant, which is also called the bracket polynomial for rational tangles, and then we will generate the polynomial up to 0 and infinity tangle. We will see what this means. And then the conductance invariant is defined using this polynomial invariant, and that is the ratio of the coefficients of 0 and infinity tangle. We will see where it gets. So first of all, I am not sure if I have defined 0 and infinity tangles, so we'll just look at that. So 0 is just an untangled state basically. This is a 0 tangle, and since this is horizontal, we can write T0. And the infinity tangle is just the vertical counterpart. So as you see that this is T0, and we saw that if we write this, what we mean is that we rotate it and we take a mirror image. So if we rotate it, we will get this. So 1 by T0. So that basically defines why this is called an infinity tangle, because this, I mean, we can't really write this, but it means that this is the infinity tangle and this is the 0 tangle. Moving on, first of all, we need to recall that what do we mean by an invariant. So Reidemeister moves were given to us that tells us that if these three moves are applied to a tangle or to a knot, it remains ambient isotopic. It does not change the equivalence class of the knot. So any function, if we define any function or any association with a knot, let's say you assign a number, in last time we assigned a fraction. So what we checked was that the fraction was invariant under these three moves. So that is the association we want to build here. To do that, we'll define something called the skein relations, and these are just recursive relations, and we will take this at the face value. For now, I'll not discuss where these come from or what the proof is. So first of all, if we are given any diagram D of a knot, then skein relations are defined as if D is a simple closed curve, that is, if you have this, then the angular D would just be 1. Okay, so this is for the simple closed curve. And then if D is a disjoint union of a simple closed curve and another diagram D dash, let's say if this turns out to be a diagram, okay, for some reason, then D would just be delta D dash. Okay, and the notations are, if this is the diagram D dash, then this is delta D. Okay, so if your diagram is a disjoint union of a simple closed curve and another diagram, then you can just multiply it by a factor of delta. Okay, we'll define what delta is later. And for any given diagram D, how do we generate this polynomial? So what we do is that if we have let's say we have the trefoil knot. Okay, so what we do is that we look at each of its crossings one by one. So what we do is we take the crossing and we can smooth it two different ways. We can remove this and smoothen it either like this, right, or we can do this. So we associate different factors with each of the smoothing, and we recursively keep doing that for the diagram. Now this is the diagram we obtained, right? So we choose another crossing in the next step and we do it again. We'll look at an example as well, but now if we want to generate any, like as we had seen before, that Reidemeister moves help us define an invariant in a way. It helps us generate an invariant. So whatever invariant or whatever polynomial this thing generates in A and B in the ring ZAB, that polynomial needs to be invariant under the three Reidemeister moves, right? So we'll try and achieve that. So first of all, the first Reidemeister move. So the smoothing is of two types. We can do this or either this. Now, as we had seen before in the second skein relation, that if it is a disjoint union of a simple closed curve and another diagram D, we multiply by a factor of delta, right? So we have A plus delta B, and if the twist is in the other direction, then it's B plus delta A. And the second thing is that if we look at the second Reidemeister moves, what it does is that it pulls apart, right? So this whatever invariant this generates, whatever polynomial this generates, should be equivalent to what this is, right? So how we get here is that we recursively apply the smoothings to different crossings. So if we first look at here, and this thing is joined this way and this is upward, so we get this first diagram and the second diagram, and then again we choose the crossing that is up there and we alter the diagram again. Okay, similarly applying the skein relations recursively, what we get is a square plus delta AB plus B square times this thing plus AB times this thing. Now we know that this is equivalent to that by the Reidemeister move, so this AB should be 1 and this should turn out to be 0, right? We'll look at it what the values of AB turns out to be. But for the third Reidemeister move, we observe that through all this process we get the same thing. Either we have this diagram, okay, or even if in the third Reidemeister move all we do is we pull this downwards, right, and we get the same thing back again. So it shows us that under skein relations, third Reidemeister move is already invariant. It doesn't change. What I mean again is that this diagram and this diagram needs to generate the same polynomial, and they do. This turns out to be same as this one. So the only thing we need to check is that if we can, the only thing that we need to impose is invariance under the second Reidemeister move and the first Reidemeister move. So for that we have the equation that AB is equal to 1, so we can simply have B is equal to A inverse, okay, and your A square plus delta AB plus B square, which came from here, we don't need this one. This is not equivalent to that one. So this needs to be 0. So from there we get delta is equal to negative A squared minus A negative 2. And for the using these values, we get for the type 1 Reidemeister move, we have negative A negative 3 or negative A power 3. Okay. So using the second, we already have invariance under the third Reidemeister move, and using these values we have invariance under the second Reidemeister move. But the first is a bit of a problem still, right? But the important thing to note here is that this is just a multiplication by a factor. So if we can normalize our polynomial, then we have invariance under the first Reidemeister move. To account for that, we'll define another thing which is called the right. The right is the sum of signs of crossing of t according to the following convention, which is just this, that if to remember this, all we need to do is that we need to turn it in the direction of the overcrossing, and the shortest distance, if it's clockwise, then it's +1, and if it's anti-clockwise, then it's -1. Okay. Now, the right is found to be invariant under the second and the third Reidemeister move, but it's not invariant under the first Reidemeister move. So, with each flip, basically, if you have this, as you can see that you have to move clockwise, so this is +1, and this you have to move anti-clockwise, so this is -1, right? So the right turns out to be 0, and if you remove the crossings, if you pull them apart, the type 2 Reidemeister move, this turns out to be 0 as well. So it's invariant under the second Reidemeister move, and similarly, if we look at the third Reidemeister move, it just gets pulled down here, so it doesn't really change the right. But if we have the first Reidemeister move and if we pull it, we get a string. So this will have a 0 Reidemeister move. I'm sorry, this will have a 0 right, but this one, if we have the directionality, this will be -1. And if we keep adding these twists, then we'll have more right. So basically, the right can account for the number of loops or number of the first Reidemeister problems that we have. So all we need to do to make the bracket polynomial invariant under the first Reidemeister move, we just need to multiply it by a factor of -a⁻3 negative right of the diagram. So this gives us one of the famous polynomials called the Jones polynomial. This is more of a combinatorial way to reach there, but yeah, so this gives us a Jones polynomial, but we do not need Jones polynomial for our talk, so we will step back and get back to the bracket polynomial, and we will find a different way to actually account for the type 1 Reidemeister move for our conductance invariant. So bracket polynomial, what we define for the invariance under second and third Reidemeister move, that B is to be A inverse and your delta is -a⁻2 minus a⁻2, right? So this is our bracket polynomial basically. So of course we noted that it's not invariant under the first Reidemeister move, and an example of a bracket polynomial for a trefoil again is we take this crossing and we smoothen it either this way or this way. Since it is not invariant under the type 1 Reidemeister move, we cannot just twist it and generate a closed curve. It needs to remain this way. So doing it recursively and we follow the path, we get our polynomial, which is -a⁻3 -a5 plus a-7. Another way to write it is this, in more of an equation form. So again, what we did is that we smoothened it recursively. But for tangles, we define it a bit differently. For knots, you see that the untangled state, the final state, would always be a simple closed curve, right? When you have smoothened all the crossings, you can either get this or n many smooth closed curves. But for tangles, you see that you can either get an infinity tangle or a zero tangle. That is the untangled state for the rational tangles basically. So for that reason, we have to stop at the infinity tangle and the zero tangle when we are recursively applying the skein relations or the relations for the bracket polynomial. So alpha t and beta of t for a particular tangle are obtained by simply recursive application of the formulation of the bracket polynomial. And now to generate a new invariant out of it, which we call the conductance invariant, what we do is that we define the ratio of the alpha of t and beta of t. Now how this helps is that since for the first Reidemeister move we had just to multiply it by a normalizing factor, and the normalizing factor for the tangle would be the same, right? Either we get alpha of t or beta of t. So that is why when you take a ratio, then you have invariance under the first Reidemeister move, and under the second and the third Reidemeister move it is invariant already because we have the bracket polynomial, right? So RT of A gives us invariant for our tangle, okay, which is invariant under the all three Reidemeister moves, and this theorem just captures that. Now as we seen that A can be anything, right? For our conductance invariant, what we do is that we define A to be root of the imaginary number iota, and therefore your B is basically A inverse, so this will be 1 over root of iota, okay, and your conductance invariant would be defined as the ratio of the alpha of t and beta of t, and the variable A would just be root of iota, and and we multiply by a normalizing factor negative iota.
So this is just a trick to make delta 0?
I'm sorry?
Is the convention to make a I just a trick to make delta 0?
Yes, sort of, yes. And the original formulation of conductance invariant comes from electrical networks and everything, so I'm not very familiar with that, but this is not the first time it pops up. And like the root of iota also helps us prove these properties actually, so we'll see what happens here. And plus it generates a rational number for rational tangles. So our conductance invariant would be this negative iota RT of root of iota, okay. Now we explore some properties of the conductance invariant. So the goal here is that, I'm sorry, I need to state this again, that the goal here is that we need to show that the conductance invariant, this C of t, generates the same value as the fraction. So what will happen then is that since conductance invariant is the same for ambient isotopic tangles, that will mean that the fraction is also the same. That will prove our second direction of the Conway's theorem, okay. To have that, we will look at some properties that are similar to what the fraction would have, right? The first one is that if you have a tangle T, and this is basically you rotate the tangle T by 90 degrees and you take the mirror image, right? So the conductance invariant of T would be just this, okay, but complex conjugation. And the second is just the distribution. Okay, so the first property follows from the case that as we defined the 0 and infinity tangles, the 0 tangle look like this, and the infinity tangle is just 1 by 0 tangle, right? So because of that, and because of that, we can generate this equation here, and what 1 of t does is that it rotates the tangle, so it will rotate the 0 part to a infinity part, and the mirror image causes complex conjugation. To look at it, I have an example. To understand it, I have an example. So if we were to look at this, tangle, okay, and to generate the conductance invariant for this tangle, what we'll do is we'll apply the skein relations recursively. So what we get is that A, and let's say we are looking at this one, okay, and the diagram we get is that for A it's always that you smooth to your right side for the undercrossing. So it looks according to the convention, so it looks like this. Plus B, and so for B we have the different kind of smoothing. Okay, and then we'll apply the bracket polynomial again. So what we get is that for here you can smooth it either this way or you can smooth it this way, okay, plus this part B you can either smooth it upward and you can either smooth it this way or is this visible or legible? Okay, okay, so this will just be this, okay. Now this will end up giving us A, this is a disjoint union of a closed curve in the tangle, so this will be delta, and this what remains is the infinity tangle, so A delta infinity, and then for the second one this is again the infinity tangle, so B infinity, and this one we have A infinity again, we have B A infinity tangle, and this is the zero tangle for us. So this is B0. So what we end up having is A square delta plus BA plus AB times the infinity tangle plus B square zero tangle, okay. So this is the bracket polynomial for the rational tangle that we have, and the conductance invariant would just we'll wait before we get the conductance invariant. So if this is T, then then 1 over T would just be the rotation and the mirror image. So it will look something like
That's just the rotation.
yeah, that's just the rotation, and now we take the mirror image. So this is 1 over T, okay. Again we apply those recursive relations and all of that. For this one what we get is, do you want me to do it recursively or should I just skip to the final thing? Would it help? Huh? Okay, so so what we get for that is the A square infinity tangle plus B square delta plus AB plus BA. So what happens is that, and for the t, I'll write it here actually. For t, what we have is this. A square delta plus AB plus BA and the infinity tangle. So what happens here is that this gets replaced and we have complex conjugation. And we know that A is root of iota and B is 1 over root of iota, and these are complex conjugates. And we also know that omega square conjugate is omega conjugate squared. So this, as you can see, is a complex conjugate, and similarly this one. Okay? So we have this equation with us, and now you can see that C1 of t by definition would be negative iota and beta of t complex conjugate divided by alpha of t complex conjugate, and you just have to multiply it by iota on the numerator and the denominator, and what you end up having is 1 over C of t complex conjugate. So that proves our first property. For the second one, we have that the conductance invariant distributes over the two tangles, over the sum of two tangles. So if the first tangle bracket polynomial looks something like this, a infinity plus b 0 and t is c infinity plus d 0, then the proposition is that we need to show that the sum of these two tangles would generate a bracket polynomial that looks like this, ad plus bc infinity plus bd 0. Why specifically this? Because the conductance invariant of Ct plus S would look something like this. For this one, this basically turns out from the simple smoothing again. So what happens is that we have this as the sum of the two tangles, and if we have completely smoothed and found out the bracket polynomial for the t tangle, what we get is a times this diagram, which is the infinity tangle, and this is the zero tangle sum S. Is this okay, the first step? And then we do the same thing to the S tangle. What we get is that we have the infinity tangle instead of S, and we multiply by C, and with D we have the zero tangle. Okay? Now this is just the, again, a disjoint union of a closed curve and another diagram, and okay, and these are just infinity tangle and this is just the zero tangle. So what we end up having is that AC of 0. Now delta is 0 as we had seen for A is equal to root of iota. So this turns out to be 0, and what we end up having is AD plus BC times the infinity tangle and BD times the zero tangle. So that proves this CT plus S for us.
So you kind of needed the operation 0,
yes? Yes, for this, yes. So now note that for the, as we had seen for rational tangles, that you can build tangles using just the integer tangle t1 or t minus 1 basically, right? For t1 we see that c of the integer tangle t1 is simply 1, and for c minus 1 is just negative 1. So that tells us that for any rational tangle our c of t would just be real. So we don't really need to worry about the complex conjugation. So C of 1 of t is just 1 over C of t, conductance invariant of the tangle T. Now, using these three properties, that C1 of t, C1 over t is a 1 over C of t, and the sum is distributive, and C of negative 1 is negative 1, C of 1 is 1. This is basically the definition of our fraction, right, for any tangle. So this helps us iteratively generate the same continued fraction form for each tangle, and therefore it proves other direction of the Conway's theorem, that since C of t is invariant for a given tangle T, this means that if the conductance invariant is the same, the fraction is the same as well. So that proves our Conway's theorem, both the directions, and we have time for the application. So in the application, we will talk about site-specific recombination. And
is this like the way that it was initially proved with the reverse direction? Because the forward seems a lot easier, not more straightforward.
Right. Actually, Conway gave the theorem without proof.
Oh.
So this is one of the first proofs. This is by Kaufman and J.R. Goldman.
Did he claim that he had a proof, or he just said, I think this is true?
He just said it's true. And it turned out to be as well. It was, for them, it was very simple to see. And he mentioned it in just a conference, and it got recorded, and then Kaufman saw it and tried to prove it using this combinatorial ways.
So these invariants already existed by the time Conway.
Right, right. The forward direction did not exist. They formulated all of those ways to actually manipulate the tangles and get the fraction out of it, but the conductance invariant already existed. Okay, so site-specific recombination. So the model that I am going to explain operates under a lot of assumptions here, that there is no, for those who know, that there is no supercoiling of the DNA, and we consider that in what happens in recombination is that the enzymes basically cut the DNA and cut the DNA sequence and rejoins it somewhere else in a different way. Site-specific recombination, in this, we assume that the enzyme acts on the same spot again and again and generates the same result. So this is the assumption under which we are running here. And let's say if we'll define a few terms. Let's say this is your substrate, and I'll put the definition here. Now, substrate is the original molecule on which the enzyme is going to act, and it will look something like this, for example. And we are assuming it's circular, if DNA is circular for us. And then we define what we call a tangle site. Tangle site is basically where the enzyme, we assume the enzyme is going to act. So here the enzyme will act again and again and generate some kind of recombination. And recombinase is just, recombinant is the tangle, recombinase is what acts on it and generates the recombinant. What I mean by a recombinant is that, let's say the enzyme acted and cut this up and generated this thing here. Okay, so this is a different molecule from the original one. And the last is that the product. So this is the recombinant, but this whole thing is our product. These are just the running definitions that we have. Now the model. The model says that since it's acting on the same spot again and again at the same tangle site, we can have recursive addition basically of the same tangles. So if S be the substrate and T be the tangle site and R be the recombinant, and the series of product that we obtain from each action is P1, P2, so on up to Pn, then it can be represented like this. N means just the fraction of this thing. S is the substrate and T is the tangle site, which we originally had like this. Okay, and if the recombinant acts once, we get the first product, and then it acts again, we get the second product, and so on and so forth. The assumption is that it will act in the same manner. It may not, but oh yeah, it's supposed to be P2. And therefore, since we had for our fractions that if we have A plus B, we can simply write this as f of A plus F of B, right? We can use that here. How is the question. So the thing is that when you have, like, how the experiment is run, basically a rundown is that you have a sample, all the circular DNA is in a sample, and you get the enzyme to act on it. You can get multiple different, like the same, like enzyme can act twice or thrice, and you can get multiple different products. Let's say all these products are P1 up till Pn, and you can run a gel. If you know what a gel is, you basically extract out different products according to their weight, and then you observe it under the electron microscopy. So what that tells us is that it gives us each of these products. Now we know what P1, P2, so on up to Pn is, and using that we can actually find out what the original substrate was and what the enzyme did to the substrate. Okay, an example of that is that, let's say, with the recursive successive rounds of recombination, we get these two products. This is what we observed under the microscope. Okay, and like for us right now it's easy to distinguish between the two and we find out, but in an experimental setup there may be many different products with us. So let's say your S represents the fraction of the substrate and R represents the fraction of the recombinant, and then from the above diagrams we see that this thing is just this fraction. So the first product is this, right? Yeah, orientation flipped. There's one more. So yeah, this is what we have in the diagram there, right? And if you can observe that if we have this tangle here, okay, so this is the tangle that we have with us, right? So this is just
Hey, sir, I don't know how much computation you're going to do with it, so I just want to let you know, I think the last two blocks,
yeah.
I think you can, I think the orientation is something else.
Oh yeah, yeah, the bottom, this one is, yeah, this is okay now, I think, right? Yeah. This? Yeah, we have this here. Okay, so it looks something like this. Okay, so this is the tangle that we have. Now this is just the vertical integer tangle that we know as T3, and this is just the horizontal integer tangle T minus 1. This we can represent as 1 over 3, as we had seen for the fractions. The fraction of this would be 1 over 3, and for this will be minus 1, so this is just negative 2 over 3. And for the second one, similarly, we get negative 5 over 3, and we know that S plus R is negative 2 over 3 and S plus 2R is negative 5 over 3, and just using these two equations we can get what the substrate looks like and what the recombinant looks like. The substrate is just the 1/3 tangle, which I have already used, and the recombinant is just the -1 tangle, the horizontal tangle. And this theorem basically captures all of the process. That is, if given a sequence Pn of rational knots and links, and the fraction is defined as this, n of s plus nr, then let pqr be such that r is a recombinant here, and the fraction, the recombinant is this r tangle, and the fraction of the substrate is p over q, then p over q and r are uniquely determined if one knows the topological type of the sequence of unoriented rational knots. What that tells us is that if we know the fraction for the products, then we can generate the fraction for the substrate and the recombinant, and hence find out what that enzyme actually does to the substrate. So that is one of the applications. This is a very crude way to actually describe a very simple example of it, but yeah, this is just the basic model of how they can actually find out the mechanism of how the enzymes work on a substrate.
So here, so here the substrate is 1/3, right? So we kind of assume that wherever the complexity is, there's the part where there's complexity, and there's a part where it's just like
right.
The loop kind of closes.
Right. Okay. It can also be here actually. I mean, if this were closed, let's say this can be a tangle site as well. This can be a tangle site as well. So you just have to, like, for the sake of simplicity, I just got the other one. The tangle site can be any, but the site specific recombination tells us that the tangle site would be fixed, because the enzyme will act on the same site again and again. So that is the assumption I had. Does that help?
Yeah.
Okay. And that's all. Okay, yeah. Thank you. If you want to read more about it, about knots, then of course, as I said before, there's Colin Adams' book, A Very Elementary Introduction, and the paper which I used for this talk was by Kaufman and Goldman on rational tangles. And if you want to know more about the applications of it, then Sofia Lambrepolo and Kaufman has another paper. This one, I can send these links by email if you want. And if you want to get into knots properly, knots and links, then there's Rolfson's book. And David Sumners was one of the first persons who started this application part in DNA and everything. So untangling DNA is a very nice paper of his. It's an article, basically exploratory article. So it will be an easy read if you want to just explore something. So yeah, thank you.
Any questions?
Yeah.
I had one very quick question.
Right.
Can we use the same idea to explain when a substrate is broken down into products, or is this only when they're combined into one product?
Broken down how?
So like sometimes when you have an enzyme acting on a substrate, it can break down into several products, right?
Okay.
And can this be modified to work on that, or?
I'm not familiar if it can be, because I just know the one part, that is the site specific recombination, and it assumes that the substrate remains intact. Sort of.
I think you can somewhat generalize the model just by taking two different sites of recombination. Because if you want to break something down, you use two sites, and maybe you look at one site first, and you use the same model, and you look at the other side.
And then so then they both close and then they separate.
Yeah.
Okay.
So maybe you would need two sequences of products. One where it's only the first site breaking down, the other one is the third site.
Right,
I had a question.
Yeah.
So you did a master's thesis on topics, right? Is this like related to your work, or?
Somewhat, yes.
Somewhat, okay. What can you tell us just a brief idea of what you did?
My master's thesis had actually 3 parts, and the first one was that, like, we saw the Jones polynomial, right? So we looked at a graph theoretic formulation of the Jones polynomial. So we try to associate to each knot another graph, and using that we find out the Jones polynomial. And like my thesis title was that combinatorial approach to knot theory. So we looked at 3 different combinatorial approaches. One was towards the Jones polynomial, one was this rational tangles, and the third one was looking at the colorings of the knot. So that involved another polynomial called the Alexander polynomial and Fox colorings and all of that. So it was a bit all over the place, to be honest. But all 3 had applications in biology actually. So that is the connecting part there.
So was your thesis like based on the application? The motivation was the application?
The motivation was the application, and for the good thing about application is that you can look at you can just look at the combinatorial structures and build models on that. You don't have to, like the Jones polynomial, Alexander polynomial, all of these things were not originally formulated this way. Like it involved I think for the Jones polynomial it involved analysis and operator theory. If he knows better, I think. Right.
There was a representation from Wills to limit the appendix that's the Jones. And then Kaufman comes up with using the bracket polynomial he constructed the Jones polynomial. That was a complementary.
So that is the attractive part for me in knot theory, is that there are a lot of combinatorial ways to actually reach some of the very difficult
that explains why
results.
polynomials are really good at holding information.
And sorry?
That explains why polynomials are really good at holding
Right.
information.
Yeah. So yeah. Anything else?
Thank you.
Thank you.